Keep your fingers crossed, ladies and gentlemen. IT was in here yesterday. Tell me the tech might be working now. So, I sent this morning. I am in still the process of writing your exam, so I don't have it written yet. But this is what I consider to be a fairly good first pass of a study guide of things I want you to be able to do by hand, and then things I only want you to be able to interpret. So you won't have to do notice that a standard deviation calculation is not up here in this list. I'm not expecting you to be able to do that off the top of your head, even with a formula, with a calculator. No, don't bother. But then down here's a list of things I want you to be able to interpret and know what they mean or how to find, even if we don't actually have formulas that are required for some of these things. If you have questions about the exam, you should be emailing me. We should be looking at talking to the tutors or to me or to somebody. Yes, sir.
Will the formulas be on the...
Those should be up here. In one sense, statistics is the analysis of what has happened. And all of what we were doing with our examination of data, with our numerical descriptive statistics, is looking at what had already occurred. So, what if I don't know what's going to occur? How can I make some predictions moving forward? Descriptive statistics, again, we deal with the data we already have. Analysis of that data allows me to build predictive models. I have to start with the ideas of what could happen. And that's what probability is. In one sense, from a strictly mathematical perspective, a lot of this can be done in calculus terms. We're not going to do any of it in calculus terms. But there's a lot of underlying calculus hiding in here. And again, we start with a bunch of terminology. Somebody give me a description, definition for a random experiment. What do you think a random experiment is? Thanks, but that doesn't help me. Yes, an experiment that's random. Circular definition. See, circular definition. I like that. In one sense, yes, something I want to figure out. But in another sense, it's something where I'm going to do this thing, and I don't know what's going to happen. So it's an experiment. I'm going to go do something. I don't know what's going to come out. You've seen a lot of these. Ready? What is it? You sure about that? What are the chances? That's the question, right? Probability examines what could happen as a result of the process we do where we don't know what the outcome will be. So if I tell you, roll the die, you don't know what number's coming up. If I tell you flip the coin, you don't know what's coming up. If I tell you pick a card, you don't know what's coming up, right? But I could make a list of possible outcomes. If I create a list of all the possible outcomes, that's called the sample space. It's really the set of things that could happen. So, if I'm flipping a coin, a normal coin, right? Head on one side, eagle on the Statue of Liberty on the other. What could happen? And therefore, there are only 2 items in my sample space. Those 2 events are my complete list of outcomes. If I tell you to roll the die, what's your sample space? The numbers 1 through 6. But those are separate individual numbers, right? If I ask you to go out and measure somebody's height, well, then it's a matter of how many decimal places you want to go to, right? So we have 2 different types of sample spaces. Based on our numerical or categorical data, we have continuous and discrete. Our die is a discrete sample space because it's a discrete idea. Height is a continuous idea. The coin is a discrete idea. The pick a card is a discrete idea. Now again, I'm assuming that's a fair die. And if it is a fair die, my results from 1 through 6 are all equally likely. But sometimes, if you create a more complicated experiment, you could come up with a list in your sample space where the outcomes are not all equally likely. I'm going to change our dice. Here are 2 of them. Roll them both, add the total spots. I rolled a 5. What is your sample space? Aha! Oh boy, let's try that again. S equals 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But those outcomes are not equally likely. Why?
Only get to the whole one way, but like,
Yeah, there are a lot of different ways to get a 6, right? I can get 6 like that. It's kind of hard to see on these dice, but there are actual numbers written on the dice. So there's another 6, but it's different. And here's another 6, but it's different. So there are lots of different ways to roll a 6, but there's only one way to roll a 2. There's only one way to roll a 12. However, I could take equally likely simple events and combine them and say, oh, well, when I roll my 2 dice, maybe I roll a white 2 and a red 4, or maybe I roll a white 3 and a red 3. Those are equally likely. There's only one way to do each of those, but both of those can be put together to make a compound event. How do I roll a 6? Now, there are more ways to roll a 6 than just those 2, so I'd have to look at a different sample space of things that were equally likely to build that compound probability. The very first question in this section of the textbook talks about, going to Barnes & Noble and buying something. You can make a purchase of a book, electronic media, or other, and you can pay with a Visa, MasterCard, or American Express. What's your sample space? First of all, this place isn't going to do as much business as you think it is. A lot of people don't pay with anything like that. No PayPal, no Apple Pay, no debit cards. I'm in trouble. Plus, does Barnes & Noble actually sell books anymore? I haven't seen a physical book in Barnes & Noble in a long time. What is my sample space of possible purchases and payment options?
If you count other as just one,
I'm just going to count other as one category. But why 6?
way you compare the categories of stuff you can buy.
Right, but if I buy a book, I can pay for it with any of the options, right? And if I buy an electronic media, I can pay with it with any option. So really, I think I have more than just 6. Let's try and write it out. Let's think about the ways we could do things. What do you want to buy? Okay, if I buy a book, I could pay for it with a Visa card. If I buy a book, I could pay for it with a MasterCard. If I buy a book, I could pay for it with an American Express card. Keep going. What if I didn't buy a book? So I buy electronic media, and then I can pay for it 3 different ways. Or I'm only buying one thing. Then my other category is other, right? So the only option left for me to things to buy is to buy something else, pay for it with a Visa, buy something else, pay for it with a MasterCard, buy something other, and pay for it with an American Express. And that turns out to give me 9 different options in my sample space. Questions? One of the things we will have to do carefully in this chapter is list out options systematically. I wrote this list putting what you could buy first and then how you pay for it. That's not a requirement. You could do it in the other order. But even if you did it in the other order, you'd still end up with these 9 pairs, regardless of which order you had them in. Questions? Now, I will freely admit to being a geek, and therefore, I got a lot of dice. A lot of them have different sides, different shapes. Trust me, I've spent way more money on dice than I should have, and some of them are absolutely insane. That die has 120 sides. Not quite a baseball, but it would hurt. Yes. I roll it, and one of them is actually flat up. I just rolled a 54. That's the one right at the top in the center there, isn't it? Bizarre, isn't it? You know, this one's got 1 through 8 on it. This one's got 1 through 12 on it. That's easier to see if it's down there to focus on. Nope, it's impossible to read. It's too bright and shiny. There we go. 12. I need to go back and mark the numbers again. They're clear. But the whole point is that I could take this die, which has 20 sides on it, and ask you the same question and say, oh, what's my sample space look like if I roll 2 of these? What's my sample space look like for different situations? I have to come up with the methods to list everything carefully. So one of the things we will do is really describe our sample spaces very delicately. We'll get back to you. But I go to this Barnes & Noble, I want to know the next person who's going to come to the register, which of those are they going to be in? Probability itself is the relative likelihood of one or more of our events in our sample space. Now, I've used a new word, event. We talked about outcomes as the individual things I've listed. An event is a subset, some collection of outcomes. We were talking about rolling a 6, and we said that there was more than one way to do it. So rolling a 6 is an event, and getting 3-3 is an outcome. So if E is some event in our sample space S, then there are a couple of things I can guarantee you. I'm going to write P of E to mean the probability of event E. What's the chance it happens? No matter what, that number is never smaller than 0 and never bigger than 1. If the probability of an event is 0, it never happens. Probability of event is 1, it always happens. Everything else is somewhere in the middle. Chance I roll a 9 on 2 dice. You can figure it out, but it's somewhere between 0 and 1. Chance it lands on heads, somewhere between 0 and 1. I tell you to pick a card from a standard deck, chance you chose queen, somewhere between 0 and 1. If my sample space is made up of a bunch of outcomes that are all separate from one another, all different, then the total probability for all of the events has to add up to 1. When I do the experiment, something's got to happen. I don't know which event it's going to be. Now, in this case, I'm using the word separate to say that these events don't have anything in common. how do I figure out P of A? How do I actually find the number for some event? There are lots of different ways to do this. The textbook really covers three, and I think the first two are far more common than the third one. So let me go through these in order. The first way to figure out a probability is to do the experiment a bunch and count. If I want to know how many ways can you roll a 32, we're going to roll this a whole bunch of times and see what happens. We want to know how many ways can you get a queen if you pick a card from the deck. Pick a card, put it back, shuffle the deck, pick a card, shuffle the deck, over and over and over, right? That's called empirical probability. We do the experiment. This, by the way, is the definition of a batting average. You've come to bat this many times. You've hit the ball this many times. That's what's happened. I ran the experiment a bunch. I flip the coin. There's a chance it lands on heads. 50%, right? Which is 50 out of 100. Did we flip the coin 100 times? I didn't even flip it once yet. How do you know that it's 50-50? Somehow, built into the experiment itself is the assumption that this coin has an equally likely chance of landing heads and tails. Well, if those are the only two outcomes and they're equally likely, then that rule right at the top of the screen that says the whole thing has to add up to 1 means it's got to be 1/2 and 1/2. 50%, 50%. So really, this is the mathy version. And then third is what's called the subjective behavior or subjective probability. And I'm going to call this a WAG because subjective probability is based on informed opinions, prior judgments, experience, or a wild ass guess. You've done this experiment a bunch of times. You've seen what happens, or you already don't have history, but you've seen a lot of things like this. I can trust you as an expert, perhaps. I think that's the least intelligent definition of probability ever used, but it's out there, and the textbook is going to use it in a couple places. This is your gut feeling. What do you think is going to happen? And then can you justify it? Page 156, table 5.1. for our Barnes and Noble outcomes, sample space. Which of these three do you think I should use to figure out what the next person is going to buy and what they're going to pay with? So that would mean it is equally likely that any of those 9 could occur. If I go down to the Barnes & Noble in Sullivan, which is where our campus bookstore is, I could ask, is there something designed in Barnes & Noble that makes all 3 of those payment outcomes equally likely? Visa versus MasterCard versus American Express. Is there something built into that Barnes & Noble that you're equally likely when you walk in to choose to buy a book, to choose to buy a electronic media, or to choose to buy something else? Are those equally likely? If there's nothing baked into the structure of that store that forces those choices to be equal or to have some pre-known method, my best bet is probably to look at the register receipts for the last week. Hey, more people are using Visa than MasterCard. Next to nobody is using an American Express card. Very few people are buying books. A lot of people are buying electronic access cards for their textbooks, and a bunch of people are buying school supplies, pencils and papers and t-shirts and whatever else is in the other category. But then I could say, oh, I can use empirical probability there. And I can actually determine directly by counting. So what does B comma V stand for? Somebody bought a book and they paid for it with a Visa card. If I look at the register receipt for the last week, how many people bought books and used a Visa card? And what I can do is I can say, oh, the probability of this occurring is the number of times that somebody actually bought a book with a Visa card divided by the total number of times somebody bought anything. Because that's my experiment. Somebody came in and bought something. So how many times did I do the experiment? How many times did this particular outcome happen? As a matter of fact, if we think of what we were doing on Wednesday, I can think of this as a frequency. A frequency out of the total number of things that happened. Ooh, I have letters for those. Frequency over number of event. By the way, if I just look at yesterday's receipts, that may tell me something different than looking at the last week of receipts. That may tell me something different than looking at the last month of receipts. It may tell me something different than looking at the last year of receipts, right? The more often I do this, the larger my number of experiments is, the more of an accurate picture I will get for how often this one event occurs. And I can do this for any experiment, even one for which I have a theoretical basis already. If I ask you to go home and flip a coin 100 times, first of all, I doubt very many of you will do it. You have better ways to spend your weekend. But if you decided to actually be bored and flip a coin 100 times, would you get exactly 50 heads? Highly unlikely. But if I then asked all of you to tell me how many heads and how many tails you got, and I put them all in one pile, instead of having just 100 coin flips, I'd have 2,300 coin flips. I'd wager that would be much closer to 50-50. Ah. Now, I have not actually defined how we get theoretical probability in general, but we've kind of hinted at it here. If I have some way of rigging the event so that I know what the theoretical probability should be, and then I do the experiment a crap ton of times, as n goes off to infinity, n arrow infinity, we get bigger and bigger and bigger, then the actual experimental probability, f over n, gets closer and closer to the theoretical probability, p of a. Problem number one. Every time I do the experiment, I have to do it exactly the same way. So if I flip this coin, I've got to flip this coin exactly the same height, with exactly the same smack of my thumb every time. I'm not that good. If I'm looking at a purchase history, I have to have no influence over that purchase behavior. I'm pretty sure that in the last 3 weeks, more books went out of that bookstore than in the month beforehand. Why? I'm pretty sure this place was dead during July. But then the semester started, and all of a sudden there was a crap ton of books in the store. Would outside factors change my data collection? Think about the FDA trials for the COVID vaccines. We needed to move that fast. Did we have time to do 100 million experiments before we started vaccinating everybody? A lot of people got really pissed about that. He said, you're rushing this, and that's a political statement. Well, that's a different medical statement. I won't talk politics about this, but there is a problem in how many experiments I can do to figure out the theoretical effectiveness of something, because I can't do infinitely many. What if our event's not repeatable? I would like to know how many people survive a car crash. How many car crashes do you want to be in? 0, I hope. I don't expect many of you want to be in lots of car crashes. Maybe there's a demolition derby driver somewhere in this room. I don't know. That's not a repeatable experiment. That doesn't make sense to try and repeat that experiment. But if I can set up the experiment and I can write out my sample space in a way that I get elementary, equally likely events, Of course, I picked a set that was stapled together. Or I can calculate in advance the probability for each event. Then, instead of actually running the experiment a bunch, I can say, oh, how many individual equally likely events are in there out of my total? So let's suppose that we had elementary equally likely events. So in our coin flip, that was heads and tails. In our dice rolling, that was the numbers 1 through 6. And we said those are all equally likely. Then the probability of some event is going to be the number of ways I can have that happen out of the number of things in my sample space. And that's how we got that the probability of heads was 1/2. There were only 2 things in my sample space. Only one of them was heads. Assuming that is a fair die. It's not loaded or rigged in any fashion. You roll the die. What's the chance you roll an odd number? Ah, 3 out of 6. The numbers are 1 through 6, 1 and 3 and 5 out of 6 options. All I have to do is count. And in my opinion, that's actually a good way to do a probability if you have this a priori in advance enumeration of everything that's involved. And that means, unfortunately, I have to count some big sets of options. A standard deck of playing cards contains, okay, does anybody not know what a standard deck of playing cards contains? Because I have had this happen before. A standard deck of playing cards is 52 cards. They come in 2 colors, red and black. They come in 4 flavors, suits, spades, diamonds, clubs, and hearts. Each suit contains 13 varieties, 10 of which are numbered, ace being 1, and 3 of which have people on them, face cards. 13 varieties, 4 suits, 52 total. You get 2 of them. How many choices are there? Oh, crap. You get 5 of them in a hand of poker. How many choices are there? Oh, crap. This set can be really big. By the way, I had this deck pre-ordered. It's in a standard order. Each suit is ace through king. The suits are in order. This is a quote, pristine deck. If I give this to you and ask you to shuffle it, how many different possible results are there? Enough that if you did that just once, right here, right now, chances are very, very high that you will have created an order in this deck of cards that no one else ever in the history of the universe has seen before. That number is so big that if you shuffled the deck one time a second since the Big Bang, you wouldn't be 1% of the way through all the possible orderings you could get. We're going to deal with some big sets. This is why I have a computer and why I have a calculator and why I have a way around trying to list them all, and instead I just want to count them all. In a business situation, doing theoretical probability is not always possible. I don't know what's going to happen tomorrow with stock offerings for IBM, for Dow Chemical, for Apple. They just released all this new information about the iPhone 16. Their stocks should go up. Or everybody should look at this and go, oh my God, they're not doing anything original and stocks in the tank. I have no idea. So quite often, we're stuck. And that's where that third piece of probability shows up. Subjective probability means we go ask a bunch of experts. Who's been in an event close to this? I need an opinion. I need a judgment. And those of you who are sports fans have probably been doing a lot of this. How are the Steelers going to do this season? Everybody I listened to for the past month said they were going to lose 2 out of 3 of the first games. Clearly, that didn't happen. So I ask an expert, but there could be wrong, right? And this is a problem with subjective probability, in my opinion. You've got to have a level of minimum understanding. Me, I follow sports very, very, very loosely. And so you would not want to ask me about my opinion on the Steelers or the Pirates or hell, the Seton Hill baseball team. I'd be in trouble. I could give you a little more about the volleyball team, but just a little, because we did an experiment 2 years ago with Riley Rock, and that's the paper that's getting submitted on Monday. The one I showed you earlier with the charts and stuff. But this much. But I need some level of experience and information to make that subjective piece work. But that means most of the time, I'm either going to do things empirically, if I can, or theoretically. And that means I should look at the rules for how probabilities work. If I'm dealing with theoretical probability, then I'm counting things, and I'm counting sets of things. How many ways could this happen? What are the possible outcomes? What's my set look like? So a lot of the rules I'm going to come up with are based on the rules for set theory. And again, that's a geek class that you may or may not have ever taken or talked to anyone about. So I need to go over some basic ideas in sets. Our sample space is a set of outcomes, a list of things that could happen. An event is a subset of this. Okay. If I think of my set as a box containing all of the things that could happen, then my event is a subset in that box. The name of this type of picture. It's not one of the graphs we've done yet. It's not a statistics picture, unfortunately. In sets, that's a Venn diagram. How many of you have heard that term before? Okay, good. if this is the set A, this little circle inside this box, all the other stuff outside the circle, still inside the box, is called the complement of A. S take away A, usually written as A prime or A bar or A with a superscript C, is called the complement of A. I think our textbook uses prime. The three other textbooks I've taught set theory out of use bar and C, which is why I wanted to make sure you'd seen those as well. So here's a question for you. How can I think about the probability of A prime? We go back to the previous rules I'd looked at. First one was that probability had to be between 0 and 1, right? Could be 0, could be 1, could be anything in between. What was the other one? It's about a page and a half back. Y'all wrote it down. At least I hope you wrote it down. People take notes. What was the second rule? The first rule was about the numbers being between 0 and 1. What was the second rule that I mentioned earlier? Yeah, the thing with separate events. If I add up all the events, all the separate events, it's got to add up to 1, right? Let's apply that to that picture. There are only 2 events in that picture. There's A, and there's the complement of A. The stuff inside the circle and the stuff outside the circle makes up the whole universe of that sample space S. So those 2 added together have to give me 1. So if I want to figure out what this one is, I know that these 2 together have to give me 1. So the chance of something not happening is 1 minus the chance it does happen. Why is this useful? Well, if there are only a few ways something can't happen, a lot of ways something can happen, I'll count the ones that are small, and then I'll solve for the other one. There are several more rules for counting probabilities that are all based on Venn diagrams. So I need to start thinking about those pictures. And if it's been a while since you've seen Venn diagrams, do about 5 minutes on Khan Academy. You'll see them all again. We'll do them a bit more on Monday, at which point your next homework assignment for Chapter 4 is due. At that point, the key will be posted right at the end of class on Monday. So you'll have all 3 keys for all the homework, plus this kind of review-ish sheet. And I will see you all on Monday. Have a wonderful weekend.